Hi, everybody. We are back, and in this segment, we are going to build, train, and test a few different classification models. We're going to apply it to the admissions data set that we had looked at in a previous segment using logistic regression, and we're going to compare the performance of a few other models to logistic regression by partitioning our data set and utilizing a validation set to estimate the out-of-sample error. And use that same validation set as kind of our benchmark with which to compare these other models. So let's go ahead here and we're going to load up the necessary packages. Libraries are caret, rpart for the cart library. This E1071 library for the support vector machine, and then we will also take a look at the random forest library implementation, which will actually implement two different ways, one with the caret package, one with random forest. We're using this exact same data set, the admissions data pulled from my GitHub repo. So you should be able to go ahead and read that table directly from the GitHub repository. And we're going to go ahead in this segment and just convert both admit and the rank variables to factor variables. So again, if you wanted to get a quick look at the data, you could run the head function on the data frame itself, and you'll see that we have these four variables: admit, which is binary, we have the GMAT score, the GPA, and the rank on a scale from 1 to 4, 1 being the highest, 4 being the worst, of an applicant's undergraduate institutions. These are all applicant data for graduate school admissions into business school. So let's go ahead and convert the admit and the rank variables into factor variables so that R knows to treat them and dummy up some categorical columns for us. And then we're going to go ahead and partition our data. So we're going to set the seed here for reproducibility, and we're going to use the create data partition function from the caret package in order to break the data into a 70%, 30% split between training and testing. So let's go ahead and run that here. We've generated now this in-train index, which is randomly assigned a vector of 1s and 0s corresponding to randomly chosen rows. So there will be about 70% of the rows will have 1s, and those are the rows that we want to keep, the ones in train that will define the columns, or sorry, the rows of observations that are stored in the training data. And we will do the same thing by running line number 27 by taking all the rows that were not in the training data, that's minus the in-train index here. We're not taking those rows, and that will form our test data set. You can again check the dimensions of those. You got 281 observations to 119, so about approximately 70-30 split. Just a little bit of noise there because that is a random generator doing that splitting for us. And let's start off looking at logistic regression. We ran this last time. Well, let's go ahead and run the logistic regression. We'll build the function using the training data. Okay, we're again going to feed it this parameter family equals binomial to tell it to utilize the logistic link function. So let's build the model. We'll take a look at our summary output here. Let me increase this size of that screen so we can take a look at that summary output. And we recognize, and I think we saw this in the last segment, that the rank variables were all significant. Maybe not at exactly the same levels in the last segment, because when we had partitioned the data, we wound up with slightly different test sets. So the results here may look a little bit different than in the last video segment on logistic regression using this data set. There are AIC down here, null deviance and residual deviance measures. Excuse me. We can generate our confidence intervals. We had seen before, raising them to base E in order to generate our odds ratio interpretable factor measures here. Right, we saw that GPA If you increase your GPA by 1 unit, this increases the odds ratio by a factor of 2.42, the likelihood of you being admitted versus not. That ratio, the odds ratio, goes up by a factor of about 2.5 there. And we're going to go ahead and build a confusion matrix using the testing data here to get our estimate of our out of sample error. So let's go ahead and do that. And we can see here if we go up, okay, there is our confusion matrix right here. And it looks like we are performing at about 71%-ish accuracy, give or take. There's the 95% confidence interval on that accuracy measurement. So we're about 71% accuracy on the out of sample data. Okay, so that's our estimate of E out for the logistic regression. In fact, maybe we should keep track of that up here. Let's write that down. For logistic regression, had an E out approximately equal to 71%. Actually, it's let's do 1 minus that. So technically, our E out here is about 29%. On the test data, that's the accurate. Well, that's 100% minus the 71% accuracy, leaves us with an error measure of 29% there for logistic regression. We'll keep that as a reference metric for a point of comparison. Next, we're going to go ahead and we will build the classification tree. So there is a little bit of difference. Yep, I just totally deleted that metric that I wanted us to keep. Let me put that up again. Consider logistic regression. E out is about 29% there. And I want to direct your attention here to the line 45, where we're going to invoke the train control function here. It's going to tell us just a few parameters that we want to control here. So if we look, we can see here that I'm going to use cross-validation. I'm going to use tenfold cross-validation, and I'm going to tell it to save predictions as true here as part of my train control parameters. And those are some parameters we are storing here in a variable called train control that we're going to pass to the actual train function that we use to build the CART model. So let's go ahead and look at this next line here. I'm feeding quite a bit of information. So we're describing the model. I want to predict the admit variable from all the other variables using that dot. Okay, we're feeding it the training data. I'm passing it the train control variable that we had just set, which is telling it we want to implement tenfold cross-validation. Okay, and we're using this tune length parameter here, which is actually a helps I think regularize the tree. Increasing tune length here does increase a regularization penalty for the complexity of the tree. And we're using a method, rpart, that is really us invoking the CART package here in R. So let's go ahead, run 45, we're gonna run 46. Okay. But you should be able to find these code chunks on Blackboard. And then we're going to go ahead and plot the output from the cross-validation results. We're going to plot the mCART object that we just created. We're going to plot that model object. And it gives us actually some pretty interesting information here. It gives us the cross-validated accuracy results here. And it does this by changing a complexity parameter associated with the the degree of splitting that tree, the degree of complexity in the cart tree. And you can sort of see here the minimum value of the accuracy. Okay, it curves way over to the right. And it takes a dip, and we want to find the model that gives us the highest accuracy. So the optimal parameter looks like it is somewhere over here, pretty low, close to 0, between 0 and 0.01-ish, okay, in order to cross-validate that accuracy. And we can go ahead and report the best tune. Okay, what was the optimal complexity parameter? And we can see over here they're using that complexity parameter whose value is approximately 0.01. Right? So that is the result of kind of tuning or validating that cart model. And the model output for cart automatically uses the best tuning parameter from this cross-validation result. So we can go ahead now and run the confusion matrix and take a look at our out of sample error accuracy. So we can run that. And let me just increase the console window here. Let's scroll up and take a look at our accuracy. We can see here we have about a 57% level of accuracy on the test data, okay, which means we have an out of sample error here estimation for the cart. If the accuracy is 57, then our out of sample error is 43% approximately. Okay, so at this point, it looks like cart not doing quite as good of a job as the logistic regression. Okay, so logistics still our winner here in this particular environment. Let's go ahead and clear that plot out. And what we're going to do next is go ahead and implement random forest. We actually have two different packages that I'm going to implement here. The first one, we're going to use the carrot implementation. So note I'm using this train control function again in line 57. I'm going to do 10-fold cross-validation. And we're going to feed it a few different parameters as well here. So let me explain. Still, we're feeding it the model here. Admit is the Y variable, and we're using that dot to say we're using all the other variables as predictors in the data set. We're feeding it the random forest method. We're still using 10-fold cross-validation as our train control method specified in line 57. And we're having to do a little extra pre-processing here. I'm having it center and scale the data. So we're demeaning the data and rescaling it. Setting a tune length parameter here that we'll be able to think about a little bit later in terms of validation, and we're feeding it the training data. So let's go ahead and run line 57, 58. We'll build the random forest model here with some pre-processing, and we're going to print the output of the random forest model. And it's giving us here some validation results. It says, all right, we ran the random forest model. Okay, we did 10-fold cross-validation here. Okay, here's a summary of the different sample sizes utilized in cross-validation. And there was some important tuning parameters. This M try parameter describes essentially how many variables are used. I think it's different splits in the trees that are being built in the random forest. So the higher that number is, typically the more complex the model becomes. And it says here the accuracy was used to select the optimal model using the largest value. So there's another measure called kappa, which essentially adjusts for the accuracy by measuring it relative to a random guess if you have skewed data. But we're going to use the accuracy measure to validate here, and that is what R did. It says the final value used for the model is the one with M tried equal to 2. That does give a higher accuracy of 72% here on the training data with cross-validation. And what we want to do next is print the confusion matrix on the testing data. So 72% would mean this would be the best performing so far that we've seen. Okay, it would only have a 38%, a 28% error rate. But let's check its performance on the test data. Okay, so we ran line 60, the confusion matrix on the random forest model here. And it looks like our accuracy on the test data is a little bit lower than 72%. It's around 70%, which means that random forest here is giving us an out of sample error. Let's call it random form 1. Yeah, is that what I want to call it? Oops, delete that. Just call it RF1. Called it there. E out on RF1 looks to be around 30% here. So still good old logistic regression. Very powerful algorithm, by the way, logistic regression. Used very, very frequently in practice. Still performing the best out of the other classification algorithms. By the way, all these other ones, aside from logistic regression that we're running here, apply also to multi-class problems. So if you have more than 2 classes, these other algorithms may be better alternatives than just trying to force, creating multiple logistic regression algorithms for each class and then choosing between those. These other classification models may work out better in the multi-class setting. So we're going to go ahead and implement another random forest package here. This is using the random forest package implementation. So we'll call this one RF2. We're just going to straight up train it. Same model here. We're using all the other variables to predict. And we can look, and the output here is a little bit different. Okay, it gives us an out-of-the-box error rate. So this is saying we are 73% accurate on the training data. Okay, and here is the confusion matrix, and this is on the training data. Okay, and you can see here it grew 500 trees, number of variables at each split was 1 variable. We can probably tweak those parameters if you wanted to by feeding it different arguments. So you can play around with this one. There's more you can control inside of it than what I'm showing you here. But let's go ahead and test the model by running it against the test data, right? The error rate on the training data was 27%, which would mean this is our best model yet if that was also the error rate on the test data, but we know it's going to be probably a little higher. So let's take a look. We are getting an accuracy on the test data of, unfortunately, only 66.39% here. So that means our error rate for the second random forest is about 34%. Approximately 34%. So still not beating that logistic regression. And that brings us to our last culprit for the day, the support vector machine. And it turns out we need admit as a factor and rank as a numeric variable. For this one, it's a little finicky in R here, so I'm going to go ahead and transform those back. And I have to do this in both the training and the testing data set. So admit is a factor. And actually, I think already was, so we may not need to do that. But we do need to coerce the rank variable back to numeric data. And we're going to go ahead and run the E1701 package implementation. I think that's what it was. Yeah, that's 1071. dyslexic and now I typed that 1071 package implementation. And we're going to do that by running the SVM function. And again, we're feeding it the model. Y variables emit, tilde, the dot tells us we're using all of the other variables as input data. And we're doing this, we're building it from the training data set. So we'll store that in SVM1. And then we're going to go ahead and test SVM1 here. And let's go ahead and test it. And look at how we're predicting out of sample. And we actually will be able to tune the SVM and validate some parameters of it to improve potentially a little bit. Let's take a look at how we're doing out of sample with the SVM. So it looks like the accuracy is at 71%, okay, which means we actually have a tie here with the logistic regression out of sample, which also has a 29% error rate. That's 100% minus the 71% accuracy. But let's see if we can improve that. So the SVM package that we're using, this E1071 package, allows us to tune it. And there are two parameters you can tune. There's a cost parameter, and there's another gamma parameter that you can tweak related to model complexity. And remember, the model complexity of support vector machine is really related to the number of support vectors that are bounding the margin. Okay, so we're going to tune this by checking through 3 different values of the cost parameter and 3 different values of this gamma parameter. Okay, and we're telling it here the X variable is all the variable in the training data columns minus the first column, and the Y variable that we're predicting is the first column of the training data. Okay, we're using the square brackets subset, square brackets to subset here. So we can run SVN tune, and then we're going to print the results of the tune, and that'll tell us here what our optimal cost and gamma parameters are. And keep in mind, if you keep rerunning this without setting the seed, it's cross-validating. It's picking different data sets, right? It's resorting different data sets from your training set by resampling. You may not get exactly the same cost and gamma recommendations every time here, but it tells you what your best performance is and which parameters to use, and that allows us to come down to line number 88, and we can retune. So I can choose which cost parameter I want, which gamma parameter I want. So we'll go ahead and retune it, and then we'll take a look at the confusion matrix of the retuned model. And we can see here the accuracy, we got to creep up just a little bit more, up to 72% on the retuned model, compared to, I believe it was only about 71% on the model that we had not tuned here. So it looks like our winner for this exercise is the SVM. Out of sample error here in terms of 100% minus the accuracy was at 28% compared to the others. And if we were doing model selection based on out of sample error, then we would want to go with the SVM here. Okay, we validated it on that testing data, and that one did perform the best out of all of them. So that wraps up this segment. Hope you enjoyed. Stay tuned.